How does SNR impact modulation techniques? Imagine trying to have a clear conversation in a noisy room. The louder the background noise, the harder it is to understand each other. In the world of electrical engineering, a similar challenge exists when transmitting signals. The key factor here is the signal-to-noise ratio, or SNR. SNR compares the power of the signal you want to send to the background noise present in the channel. When the SNR is high, the signal is much stronger than the noise, making communication clearer. When the SNR is low, noise can drown out the signal, leading to errors and lost data. Different modulation techniques respond differently to changes in SNR. Take amplitude modulation, for example. It encodes information by varying the amplitude of the carrier wave. But this makes it very sensitive to noise because any disturbance in amplitude directly affects the data. If the noise gets stronger, the signal's clarity drops and errors increase. On the other hand, frequency modulation encodes data by changing the frequency of the carrier wave. Since it relies on frequency shifts rather than amplitude, it is more resistant to noise that affects amplitude. This makes frequency modulation a better choice when the SNR is low. Modern systems often use adaptive modulation, which adjusts the modulation scheme based on the current SNR. When the channel has a high SNR, the system can switch to more complex modulation schemes like quadrature amplitude modulation, which packs more bits into each signal. But if the SNR drops, it switches to simpler schemes like binary phase shift keying, which are more reliable but transmit data at a slower rate. This flexibility helps keep data transmission efficient and accurate. The bit error rate, or BER, is another important factor linked to SNR. As SNR improves, BER drops, meaning fewer errors in the received data. Different modulation schemes have different BER versus SNR characteristics. For example, binary phase shift keying needs a lower SNR to achieve a certain error rate compared to higher-order schemes like quadrature amplitude modulation. This means that in noisy environments, simpler modulation schemes are often more effective. Engineers need to estimate the SNR accurately to choose the right modulation technique. Noise sources can come from internal circuit interference or external environmental factors. Techniques like signal amplification or noise shaping can help improve the effective SNR, making the communication more reliable. In the end, SNR plays a vital role in determining which modulation technique works best. Higher SNR allows for more complex, faster data transmission, while lower SNR requires simpler, more robust methods. Adaptive modulation schemes use real-time SNR measurements to optimize performance, ensuring that signals stay clear and errors stay low. This balance between data rate and reliability is essential in both analog signal processing and control systems, making SNR a fundamental aspect of effective communication.